All right, everyone, Mr. Graham here. Today I want to talk about circular motion, and since we've studied a little bit about gravity, I want to use, or gravitational forces, I want to use gravitational forces to introduce circular motion. See, circular motion is the main theme of this unit. So we learned yesterday, or recently, that you have gravitational forces between any two objects in the universe. Actually, if you can see an object in the universe, there's a gravitational force between you and it. It's just you have to have very large masses in order to have an appreciable or a measurable gravitational force. And if you notice here, I do have two gravitational forces here. We learned Newton's third law says that for any force, there's an equal and opposite reaction force. So yes, I have the sun here, and it's exerting a force on the Earth, but the Earth is also exerting a force on the sun. But what I want to do is just talk about the force that's acting on the Earth now. So I'm going to turn the force acting on the sun off. Well, it's still going to be there, but we just don't have to worry about it. And the Earth is also in orbit, so if I hit play here, it's actually going to move. And if you notice, I have the velocity vector for the Earth drawn, and I have the gravitational force vector for the Earth drawn. This is not to scale, by the way, not remotely to scale the Earth. You can fit 1,000,000 Earths inside the sun. You know, you think the Earth's big, the Earth is nothing compared to the sun. And there's stars out there that make the sun look even smaller than the Earth as compared to the sun. Pretty interesting. So again, we're talking about circular motion here, and the Earth, any of you that know about astronomy, you know that the Earth doesn't actually move in a perfect circle around the sun, but its orbit is highly circular. So we're going to kind of assume that it is a perfect circle. All orbits in the universe are actually ellipses. They're ovals. Some are more ovalish than others. Some are more circular than others. The Earth's orbit is actually pretty circular, which is good because it helps keep the climate pretty regular. Now to see what's going on, to start analyzing this, I'm going to put a white background on so that, am I recording? Let me make sure I'm recording real quick. Yeah, I'm recording. So we can see a little better what's going on. I've also put a tracer on the Earth so we can actually trace its motion. As you see, it makes a pretty good circle as it orbits the sun. But what I want to talk about, and this is a big misconception or a big hard thing for a lot of students to understand, is that even if an object is moving in a straight line, or even if an object is moving at constant speed, if it's turning, if it's moving in a circle, it is accelerating. Remember, an acceleration is defined as a change in velocity over a time interval. A change in velocity. We know physics now. We know that a velocity indicates an object's speed and its direction. So since the Earth's velocity vector changes direction, we say it is accelerating, even if it's going at the same speed. And if if you know Newton's second law, then you kind of hopefully can kind of understand why this is the case. Newton's second law says that the net force, remember you can write net force that way or with the sigma symbol. The net force is mass times acceleration. Well, if acceleration is a change in velocity, and if I tell you that if an object moving in a circle is constantly changing velocity because its direction is constantly changing, then if it's accelerating, that means it requires a net force in order to cause that change in motion. So try turning your car without exerting a force on the steering wheel, which makes a force between the tires and the road that makes your car turn. You can't do it. If an object is turning, there must be a net force involved that's causing that motion. So keep that in mind. If an object is changing velocity, like I got here, then it is accelerating. If it is accelerating, then it requires a net force. Okay. All right. What's tricky is what is the direction of that net force? And it's hard to, well, we can see what is the direction of the acceleration is what I'm talking about. It's hard to conceptualize. If you're moving forward and you speed up and you're moving forward, obviously your acceleration is in the forward direction. But here I got velocity that's pointing up and I have a force that's pointing to the left. So what is the direction of the acceleration here? Well, the easiest way to determine this is to deal with the vectors and add or to do a little vector addition. And so I do need to remind you guys of something real quick. Let me move this to the side. I need to remind you guys how we add and subtract vectors. Many of you probably remember, but just in case you forgot, let's talk about how we add vectors. So real quick, if I want to add this vector and I want to add it to another vector, this one, Well, I line them up. I line them up tip to tail, and then the resultant vector will be drawn from the tail of the first to the tip of the last. So that would be the resultant vector for that vector addition. If I want to subtract a vector, though, let's say I want to take this vector. Well, let me go back to, let's say I want to take this vector, but then I want to subtract. Oops. I want to subtract another vector. I want to subtract, say, this vector. Let me name these vectors. Let's say that this is vector A and this is vector B. So I want to do vector A minus vector B. Well, what we do, the easiest way to think about this is I take vector A and then I add the negative of vector B. You guys know that if you add a negative, it's the same thing as subtraction. Now, what the negative of vector B means is just that it's the opposite direction. That green vector right there would be considered to be the negative of vector B. So I would add those. I would add vector A to the negative of vector B, which means I take vector B, the negative of vector B, line it up, and do the same thing, tip to tail. And so the vector difference between vector A and vector B would be this vector. Okay. We got to understand that in order to determine the direction of the acceleration of the object. Okay. All right. Let me move it back here to the center. And so what I'm going to do, I have an initial velocity vector here. And so I'm going to draw that so I can keep track of it after the Earth starts moving. I have an initial velocity vector, which I'm going to put here. Ooh, forget to change colors. Let's do green vectors. Let's do green vectors. So this will be my initial velocity vector. So I'm going to call that VI. And then if you're an AP, because I'm going to use this video for AP as well, it would just be V naught, the initial velocity V naught. And then I'm going to hit play and just let the Earth go for a while and then draw the final velocity vector. So let's say right there. So we'll take that velocity vector. You might say, Mr. Graham, why are you moving stuff around? You can't do that. You can move vectors around whenever you analyze them. That's one of the most useful aspects of vectors. You can move them around whenever you want to deal with stuff. So there's my final velocity vector there. And so that'll be my final velocity vector. Let me label it as final velocity vector, and I will be moving those around. But something else I want you to keep in mind, if I'm talking about the average velocity, or let's say I'm talking about the average velocity between these 2 points. Well, I would draw that average velocity vector right about in the center, right, or in the center of where they were. If I want the average velocity for this whole motion from here to here, if I want to draw the average velocity vector, it would be the one that's right in the middle, right? That's why when you sum numbers, you add them and you divide them by 2. So I'm going to divide the total distance here by 2 and draw my resultant acceleration vector from this location. Okay. All right. So again, I'm going to take, now you should know at this point that, remember the acceleration is change in velocity over the time interval. So I'm just going to talk about change in velocity right now, which is final velocity minus initial velocity. So these are vectors. So I'm going to subtract that initial velocity vector from the final velocity vector, which means I'm going to take my initial velocity vector. Well, first, let me take my final velocity vector. I'm going to take my final velocity vector, and then I'm going to subtract my initial velocity vector, which means I must draw the negative of my initial velocity vector, which would be the same thing, just in the opposite direction. And then I add those 2 vectors to each other. And so when I add these 2 vectors, I line them up tip to tail. And my resultant vector is going to be drawn from the tail of the first to the tip of the last. So that is the direction of my acceleration. So I'm going to write A there. That's the direction of my acceleration. Okay. I'm going to erase everything else now. Now I have, not everything else, but I'm going to erase some other stuff. The acceleration vector A is what I'm dealing with, and I'm going to draw it from that spot that I talked about before. So right there. And notice that acceleration vector points, let me start the simulation again. What direction does it point? It points directly towards the center of the circle. And so because it points directly towards the center of the circle, it gets a name. It comes from a Latin root name, but it gets a name, centripetal. So because that acceleration vector literally points towards the center of the circle, it is called a centripetal acceleration. Where centripetal, centra obviously means center, and petal or petal comes from the Latin root word meaning seeking, or it can be loosely translated to seeking. So a centripetal acceleration means a center seeking acceleration, literally means towards the center of the circle. And if we know an acceleration is centripetal, we put a little subscript C. So that's centripetal acceleration. It's weird. An object moving in a circle has an acceleration vector that literally points towards the center of the circle, and we've just shown that. If it's hard to understand what I went through, watch the video again, check YouTube. There's other people that will teach this as well. I feel like geometrically, though, looking at the geometry and then doing the vector subtraction, final velocity minus initial velocity to get that result, I think that's the easiest way to see. Okay. Now, how do I deal with that? First of all, Newton's second law still applies. So the net force is going to be equal to the mass times the acceleration. If my force here, which again is the gravitational force, points towards the center of a circle and the object moves in a circle, then we call it a centripetal force. And then we have a centripetal acceleration, and then we can use Newton's second law just like we have been. Okay. It turns out, though, and if you want to know why, you can take AP Physics C next year. This is a proof that we do. It does require a little calculus, so you need a little bit more math knowledge first. But centripetal acceleration is actually equal to the linear speed of the object squared divided by the radius of the circle. So when we use Newton's second law for circular motion, that's what we always end up substituting in for centripetal acceleration. The speed squared divided by the radius. Notice I'm saying speed and not velocity because the speed in uniform circular motion, which we have here, uniform circular motion just means motion in a circle where the speed doesn't change and the radius obviously doesn't change. So in uniform circular motion, the speed stays the same, but the velocity is constantly changing because, again, the direction is constantly changing. Now, if I wanted to finish this off, this vector, this force vector here is a gravitational force. That's what keeps the Earth in orbit around the sun. And so my next step here, well, I only have one force here making up the net force. It's just the force of gravity. And then when I substitute v squared over r for the acceleration, then I get mass times v squared over the radius. So this is Newton's second law as applied to an object moving in a circle due to a gravitational force. Gravitational forces are not the only circular force, centripetal forces. Circular forces, centripetal, same thing. Tension, if you're swinging around something in a circle on the end of a rope, tension could be the centripetal force. If you're turning in a circle in your car, like I already said, yes, you put a force on the steering wheel, but that makes the wheels turn, and then it's the friction that acts on the tires that points towards the center of the circle or points in the direction that your car is actually turning. So any force can be a centripetal force. And notice here, I didn't put FC here, right? Up here, I put FC because that's the net centripetal force that's causing the centripetal motion. But whenever I go a little deeper, I need to say, all right, well, that force is the gravitational force. Oops, sorry about that. It is the gravitational force, and so I indicate that as such. Okay. All right, so that's centripetal motion in general. You might have heard this word before, centrifugal or centrifugal. Centrifugal forces, and we'll talk about this. I don't want to give you too much in one video, but centrifugal forces, once you know what you're doing, or once you understand this concept, centripetal forces, even though that word is used way more often in general language than centripetal motion, centripetal forces, centrifugal forces do not exist. What do I mean by centrifugal forces? That's whenever so let's say you turn in the car. You're turning your car and you're going kind of fast. I like fast cars. So I'm driving fast and then I turn the wheel. I feel like I'm being forced out of the car in the opposite direction I'm turning. And so the name given to that sensation is centrifugal force. It's not real though. I'm not actually being pushed out to the side. I'm trying to go in a straight line and the car is turning underneath me. And so we'll talk more about that in the future. We'll watch more videos about that in the future. But understand that when someone says centrifugal force, it's literally something that doesn't exist. It's what physicists call a fictitious. Do I know how to spell fictitious? Fictitious. I don't know. It's what physicists call a fictitious force. It's a force that seems like it's real, but it's actually not real. It's just due to your sensation. Okay. So that's a general idea here. Anytime you have an object in a circle, and I'm using gravity as an example because that's what we studied yesterday. But remember, any force can be a centripetal force. Bottom line, if an object is moving in uniform circular motion, which means it's moving in a circle at a constant speed, it is constantly accelerating because the direction of the velocity vector is constantly changing. That acceleration, as I already showed, points to the center of the circle all the time. At all times, it points towards the center of the circle. And because it is an acceleration, this is an acceleration in response to a force, I can then use Newton's second law to analyze that situation, to analyze the forces and their accelerations. And then whenever I deal with centripetal forces, I always substitute v squared over r in place for centripetal acceleration. Okay, so there's a little intro. Might be kind of confusing. I understand this confusing stuff. It's counterintuitive. Most people think, well, I'm traveling constant speed, I'm not accelerating. No, if you're changing direction, you're accelerating, and that's because it requires a force to do so, a non-zero net force to do so. All right. Well, that's about it. Hope you enjoyed. Have a good one.